Next speaker is Jan Wanderberg, comes from Berkeley.
Hey. Okay. Microphone's working? Can you hear me? Good. So yeah, hey, I'm Jan van den Pont. I'm going to talk about dynamic linear algebra. And first I want to briefly explain what does this dynamic refer to. And for that, let's consider a classic algorithm. So usually when we talk about algorithms, we use the following model. We receive some input, then using the algorithm, we perform computations, and eventually we receive an output. But this classic model of computation can be really inefficient for many modern scenarios, because what does happen in the real world? Well, our input can change over time. Let's say you try to analyze a social network, then there are constantly new friendships forming, new users that register. Or maybe you have some routing task on a road network. Because of the traffic conditions, the optimal solution can also constantly change. And if you then just run your algorithm over and over again, constantly recomputing the solution, that's just going to be really inefficient. That's why we study dynamic algorithms. What we try to figure out is how can we update the solution with as little time as possible. So we're trying to find data structures that are able to maintain the solution to, well, any type of computational problem. And yeah, my research focus here is on dynamic linear algebra. So these are algorithmic techniques that allow us to efficiently handle dynamically changing matrices. So try to maintain some property of a matrix where the matrix is allowed to change over time. And I use these techniques to answer open problems in the area of dynamic graphs. So these are dynamic algorithms for graphs that keep changing, things like social networks or road networks. And I used these dynamic linear algebra techniques also in the area of optimization to speed up a bunch of optimization algorithms. So let's talk briefly about dynamic graphs. I already gave the example of social networks and road networks, but we could also consider, for example, computer networks, because servers and computers, they might go online or offline, or maybe we create new links, or maybe some link breaks. So these networks, they are all constantly changing. And you can just translate a graph into a matrix, right? You just take the adjacency matrix. And now if you have a dynamic graph, let's say one of these edges is going to be deleted, then this really just means you have to update your adjacency matrix. Put, for example, a 1 down there in the corner, a 0 down there in the corner when the edge is deleted. And this way you can translate dynamic graphs into dynamic matrices. And there actually exist a whole bunch of reductions that allow you to phrase graph theoretic problems as an algebraic problem for matrices. And using these reductions, you get a whole bunch of algorithms for graph theoretic problems. So you don't need to read all of them. I just want to point out there are a lot of graph theoretic problems which you can solve on dynamic graphs using dynamic linear algebra by phrasing these problems as algebra problems. And besides of these dynamic graph applications, I used dynamic linear algebra also in the area of optimization. So this now is not the dynamic setting. These are now classic algorithms where you receive the input, you perform the computation, then you get the output and you're done. But even though this is a static model, you still have some kind of dynamic aspects, because typically these optimization algorithms, they're iterative. Think of something like Newton's method, when in every iteration you have to solve some linear system in order to compute your Newton step. Well, since the argument to your function here is the current point of your algorithm, and the point is constantly moving, you have a dynamic matrix for your Hessian and a dynamic vector for your gradient. So this really is just the dynamic linear algebra problem, because you have to solve a linear system, but the linear system keeps changing over and over again. And yeah, using dynamic linear algebra techniques, we're then able to speed up things like Newton steps a bit. So let's talk about some results for linear programs using this technique. So if you look at something like the central path method for solving linear programs, there was a deterministic solver by Vatia back from the 80s. And since then, all improvements for linear programs have been randomized. And recently I showed that, okay, by using dynamic linear algebra, you can speed up linear program solvers and get a matrix multiplication time deterministic LP solver. And let's say you have a linear program where the 2 dimensions are quite different. You have n constraints where n is much larger than the dimension d. Then we have an algorithm that runs in nd plus d cubed time. And let's say the constraints are a lot more than the dimension, something like d square or more. Then the complexity is really just bounded by the first term nd, right? And well, if you have n constraints in d dimensions, then that's already the input size that you have to read anyway. So this is a nearly linear time algorithm. And besides of things like central path, you can also apply these techniques to other iterative algorithms. Think of something like the simplex algorithm. Whenever you move from one vertex to the next, you also have to solve a linear system. And the classic implementation of the simplex algorithm needs something like n squared time per iteration. And we show, all right, instead of n squared time, you just need n to the 1.5 time per iteration. Okay. So now these are all results for linear programs. Obviously, you can use them to solve other problems. So something like discrete optimal transport. Using these results for linear programs, we get a nearly linear time algorithm for that. We also get a nearly linear time algorithm for linear L1 regression, assuming that the number of data points that you have is at least d to the 1.5, where d is the dimension. So if you have a lot of points, you can now solve this in nearly linear time. And you can also apply this to things like min-cost flow bipartite matching, negative weight shortest paths. These things can also now be solved in nearly linear time, assuming you have enough edges in your graph, at least roughly n to the 1.5. Okay. And yeah, my motivation for the 2 programs here at Simons is that I'm looking for other interesting iterative algorithms. So if you have some algorithm in your research area where you have to repeatedly solve some linear algebra problem, it doesn't have to be a linear system. It can also be something like, let's say, compute leverage scores or something like that. Then yeah, come talk to me. Maybe we can construct some data structures for that and make the algorithms faster. Sorry. So summary, I study dynamic linear algebra. I use that for dynamic graphs to solve these graph theoretic problems on dynamic graphs. And you can also use that in optimization for iterative algorithms. Thank you.
One of the other speakers says that can you at least give us like a little bit of information about what's allowed to change?
What's allowed to change? If you can phrase it as a low rank change, then it's fine. If it doesn't change in a low rank way, then usually you try, or in past research, we try to modify the iterative algorithm a bit so that we can at least handle low rank approximations of the change. But in the end, it always comes down to trying to phrase the changes in some low rank way.